Okay, so here we're going to talk about continuous random variables. And this is a little bit different from discrete variables. If you recall, discrete are counting numbers. So like 1, 2, 3, 4, 5, etc. Continuous variables are things that could be measured. So an example of each of these might be people and gas. For example, if you're going to count people, you're not going to end up with 19.4. You're either going to have 19 people or you'll have 20. For continuous, though, if you're putting gas into your car, you're not going to jump from 19 all the way up to 20 gallons. It's going to slowly increase from 19 all the way up to 20. So it's going to be able to have all the values in between. Hence what we say when we mean continuous. We're going to talk just a second real quick about uniform distributions. And uniform distributions here, because they are exactly the same all the way through here. It's unchanging. And that means that all outcomes are going to have the same probability here. And when we talk about probability for these distributions, we're really talking about the area inside. And the total area will always equal to 1. Let's look at a normal distribution, which we talked about kind of a bell shape. And here again, the area is also equal to 1. And the probability equals to area. Kind of in short, that's really what we want to think about, that the probability equals to area. So let's look at, again, the uniform distribution here. And I just put a value of 0.10 there for no better reason. It's not going to make a difference because it's completely uniform here. Now, if I wanted to get the area between 3 and 6, well, each of those, all we really want to do is really calculate the area of this rectangle right here, because area is going to be the probability. So if you recall, area of a rectangle is length times width. So all I would have to do is multiply the length here, which is going to be 3 units wide, and multiply it by the height, which is going to be that 0.10. Now, this is extremely easy for a rectangle. If we're trying to get the area underneath one of these normal distributions, it becomes a lot more harder. And so we're going to concentrate on figuring out those areas here. All right. So let's talk about the normal distribution here. And I'm going to actually just fast forward this here. We already talked about this at the end of chapter 3 during the empirical rule. If you recall, the empirical rule told us probabilities associated with 1, 2, and 3 standard deviations out. This is very helpful, but it only gives us exactly, again, just integer standard deviations outwards. What if we wanted to know area right in between, somewhere like right about here, where we have 1.4 standard deviations out? So the empirical rule doesn't actually give us accuracy for that. We're going to want to use the actual normal distribution here, which is in fact a function here. Here's our equation for it. We're not going to worry too much about it because our TI is going to work those calculations out. But we're going to just focus back exactly how we did in chapter 3, but rather than the empirical rule, we're going to go ahead and use some more sophisticated methods here. Okay, so let's talk about the standard normal distribution. And the standard normal distribution is a normal distribution, but where our mean value, if we're talking z-scores again, is going to be 0. So the mean is 0. If you recall, z-score tells you how many standard deviations away from the mean. So if you're right at the mean, you're going to be 0 z-scores away from there, or 0 standard deviations. And then our standard deviation is going to be equal to 1, because that's the measure of z-scores here. So what if I wanted to find the area or the probability, because they're one and the same here, for a z-score that is less than 1.32. And again, since it's a decimal, the empirical rule is not going to help us out here. So let's write some notation. The probability the z-score is less than 1.32. And so what we're always going to want to do is we're going to always want to make a little sketch here. Let's draw a normal distribution. Let's label the center, which is going to be 0. And there's z-scores. And 1.32 is somewhere off to the right. I don't got to be too accurate, but somewhere off to the right there. And what I want is the area less than this. So I'm going to mark it, and then I'm going to shade all of this area below. And this is going to be very helpful for us to figure it out. So we're interested for all the area all the way up to 1.32. Now, traditionally, we would have to use these charts, and we would want to shade it just so we can actually see that our picture here matches up with the actual image that we have in this case. Because there's charts for greater than, or if it's below the actual mean, the halfway point or so. And the way this chart works is that the first decimal of accuracy is given here with a z-score of 1.3 and the second decimal of 0.02, and then we just trace where those two end up meeting, which end up giving us 0.9066. So from our table, if we wanted that area, it would be 0.9066. We're not going to really rely on tables. We're going to go very calculator heavy. So we're going to go ahead and plug this into our TI-84. And we're going to go ahead and use a function called normal CDF. And the way you input this is going to be lower, upper, the mean, and then the standard deviation. So 4 commands in this case. And so our upper, if we're looking at our picture, the upper z-score that we had is going to be that 1.32. Our lower, well, if we keep going this way, if you recall from algebra, we keep going and going, and we would call that negative infinity. We don't really have a negative infinity, but we're going to kind of use that idea. And we're really just thinking of a very, very small number in this case. So for a very small number here, let's try negative 1,000,000. How's that? And let's just write it in scientific notation here as negative 1 times 10 to the 9th. And our calculator actually writes that as negative E9. So if you've seen that scientific notation, and that E is actually the second function, and it's actually a double EE. It shows up as a single E, like this, but the actual button is an EE button. So on our calculator, you would hit second distribution and then look for the normal CDF. Now this is important that for binomials, you could have a PDF or a CDF. For our normal distributions, we're only going to use the CDF function in this case here. So we would plug this in as normal CDF, negative E9. So that's our way of writing a very small number. I'll just refer to that as negative infinity, although it's really not. It's just negative 1,000,000 there. So it's a very small number. 1.32, 0, and 1, because our mean and standard deviation are always going to be 0 and 1 if we're talking about the standard normal in this case. Okay, and from our calculator, that'll give us 0.9066. And I will post a video on how to access the normal CDF on your TI. Okay, so here's an example. I just fast forwarded a little bit here. A couple of examples for you to get familiar on plugging in these z-scores with your TI. Go ahead and sketch a graph first and then figure out the probabilities, and it's going to be a lot more helpful. So I'll let you pause it here, check out the other video if you need to, and then I'll go ahead and work through these. Okay, so for this first one, here's our normal distribution. The mean is always 0, right smack in the center, and this x-axis is representing our z-scores here. And negative 0.7 is somewhere to the left. Where exactly, I don't know. I'm just making a rough sketch here. And we want z is less than that. So we're going to want this shaded region here. So that's what we're looking for. That's our probability or the area that we want. Okay. And so if we recall, we're going to go all the way towards the bottom here. So I'm calling that negative infinity or negative E9. And for your normal CDF, you always put your lower, which is going to be this here. And then we put our upper, which is going to be the negative 0.7. Then we always put our mean and standard deviation. So there's our mean. And then if you recall, for a normal, our standard deviation is always going to be 1 as well. So maybe I'll write that down, that sigma is always equal to 1 in this case. And then it's just a plug and chug. We're going to get 0.2420. Here's another one. There's 0, 1.67 is to the right somewhere, and I want greater than or equal to. Now, in this case, if we use an inequality with an equals or not, it's not going to make a difference because technically the area of a line like this is technically 0. Or for us, it's very, very small that it could just be negligible. So we're not really going to worry whenever we have a less than symbol or less than or equals to. It makes a big difference for discrete values like a binomial. So in this case, when we do our normal CDF, our low value is a 167, and then our high value is going to be this kind of positive infinity. And then 0, 1 for our mean and standard deviation, and we get 0.0475. Let's try the case where we're going in between two values. Not yet, not between two values, but greater than. So there's negative 1.4, and we want greater than, so to the right. And so our normal CDF, our low value this time is going to be the negative 1.4, and then our high value is going to be that negative infinity there. Okay, now in between two values, between negative 0.34, and I just put it a little bit closer just to kind of be on scale, and then 1.67 to the right. And now we want the region in between. So from our normal CDF here, the low is going to be negative 3.4, and now our upper is 1.67. Notice we don't need infinity or negative infinity or that E9, a negative E9, because we're actually just restricting it, and we're not going off to the tail ends. Okay, and just another note here, if you got some of the other calculators that have the newer menu notation might show it like this: normal CDF, your lower negative 1.4, your upper E9, and then mu and sigma there. But once you plug it in, it still shows it in the other format. So I'll always write it in this format here. Okay, and now between these two values, there's 8.4, and then here's 2.43. Both of them positive, so off to the right somewhere. So this is a normal CDF, our low being 0.84, our high being 2.43, and then 0 and 1 for our standard deviation and mean there. And from our calculators, we're going to go ahead and get this value of 0.1929. Okay, so let's do one more example here. And if you want, you could go ahead and pause the video. Okay, so let's work this example out here. And so right smack in the middle is going to be 68. And this is corresponding to our golf score. So I'm going to call that my X. My standard deviation is 3. And then my mu is going to be 68. And then we're looking for a score of 65, and we want it to be less than that. So less than that 65 there. Okay. And so this is the region that we're actually looking at. Now notice they're not talking about it in terms of the standard normal. So here they didn't use z-scores, they're actually using the scores or golf scores. I always like to label both to make sure that we kind of have that consistency going there. So we have the probability X is less than 65, but in terms of z-scores, what exactly does that mean? Well, 0's in the center, and in order to get the z-score, if you recall, that's X minus mu over standard deviation, which in this case is going to be our data value, 65 minus 68 all over 3. And so that gives us a z-score of -1. So 65 corresponds to the same value as z-score of -1. So I always think of our x-axis here in terms of 2 units, the original units that we're talking about, and then also in terms of z-scores. And if you're able to think of that in both ways, it's going to be very helpful later on. So the probability that z-score is less than -1. And notice my notation that I'm referring to it in terms of x or in terms of our z-score there, because they are one and the same point on that x-axis there. So in this case, I just want the normal CDF of -E9, -1, 0, 1 in this case. However, we always converted it into a z-score first because traditionally we use those tables. Now that we're using technology, we really don't even need the z-scores. We could really just talk about it in terms of the golf scores. So the probability X is less than 65 would actually be a normal CDF of -E9, because we're still going towards kind of negative infinity or a very small value. And then 65 here, right, that ends up being our upper value this time. But the mean is going to be 68, and the standard deviation is going to be 3. So again, using these values here, and that's going to give us exactly the same probability. So it's going to be either or of those that we could actually end up using. And I'll just write a note there that we actually don't even need to get the z-scores, but it is helpful to make sure we get those. Okay, here's another problem. You could pause it and try to give it a go. Okay, so let me sketch the solution here. So we want between 66 and 70 this time around. And again, I'm not even going to worry about the z-score. We're just going to talk about it in terms of our golf scores here. So probability X is between 66 and 70. And so our normal CDF, there's our low, there's our high, our mean standard deviation, and that's going to give us 0.4950. Just make sure you're paying attention to the notation, whether we're using actual X's or if we're actually using z-scores.